Thank you. Well, as it was just mentioned, by the way, for some of you who are there, there's still a few seats here in front if you like to come and sit here. But as I said, I'm very happy to be here. I'm very happy to be here because, now I do different things. And yes, I do them, I'll show in a moment. We do them with different operations with at MIT, with a lab at MIT, both in Boston and Singapore. We do it with our design office in New York, in Turin, and in London. We do it with some of the startups that came out of them in recent years. So they were a few hundred people spread between Europe, Asia, and the US. But initially, I was born as a civil engineer. So for me, this is like, coming home. And actually, I did my thesis in Paris at the École des Ponts et Chaussées with Jean-Armand Calgarot and Michel Virlogeux. So I think Michel was actually the chairman of FIP just I think maybe 10 years ago or so. So anyway, so it's great to be here, and I still have a lot of passion for civil engineering, for structural engineering, and so I look forward to having some discussion with you. However, today I was asked to talk more about big data, and so I will share with you some of the work we're doing in this space. And I wanted to start with actually some images about the future that a bunch of artists did in France in the beginning of the 20th century. And they would imagine how life would have been 100 years later. So these were called a bunch of sketches. They were called en l'an 2000, in the year 2000. And they got some things right. So the time, and they were doing this really around 1900, so 100 years before this, and before 2000. And they saw, of course, mechanization in agriculture coming. They also got right other things. They saw the Roomba, the little robot that cleans your house. They also got something else wrong. So, they thought that actually basically the police would be like this in year 2000, or that it would move in the oceans like this, which is not really the case. Or that firemen would use this. So that, from an epistemological point of view, is related to something that many people, including Karl Popper, have written about, which is we cannot predict the future. But the future is something we can all create together. This is Karl Popper, we're all equally responsible for success because the future is what will come out of the decisions we make today, tomorrow, and so on. And maybe some of you tomorrow going out will have a new idea that will revolutionize structural engineering that will change a part of the future, of our collective future. So really what we are passionate about is doing this, exploring not the future, not trying to look at the future, but looking at transforming the present, and especially this interface. The interface is between digital and physical, between the world of the city and the world of bits. If you want, you can say that today the internet is becoming Internet of Things and is changing the way we can understand, design, and ultimately live in our cities. So this is really what we are passionate about. As I mentioned before, we are doing it with different operations. You see Sensible City Lab, the lab at MIT, both in Boston, Cambridge, Massachusetts, and Singapore, with our design office in New York, in Turin, in London, and with some of the startups that have been coming out of them in recent years. So today we can see a city like this. We couldn't a few years ago. This is actually Lisbon, mapped using billions and billions of data points collected from the taxi network. That was in MoMA, the Museum of Modern Art. It was done by Pedro Cruz in our lab at MIT. And it shows you a city like we couldn't see just a few years ago, but we can see today. A few years ago, we could see the physical city. Today, we can really see the metabolism in real time. And that's thanks to data, what we're discussing today. And then if you take this data and you analyze it, you can do interesting things. For instance, that's the same data in New York. What you see here is taxis again in New York. Every dot, a yellow dot is a pickup, a blue dot is a drop-off. Which place is this in New York? Any ideas? Come on, guys. Yes, JFK. So that's the airport, JFK. If you zoom out, you see JFK is down there. You see Manhattan and all of the boroughs. And then, you can ask yourself, for instance, questions such as this one. We started a few years ago, and we said, well, many times you're going from one place to another place in the city, and many people next to you might be doing the same route. So how many trips we could share in New York? If you phrase it mathematically, you could say, imagine you want to take everybody to their destination when they need to be there, then, how many trips can you combine? And if you look at this, between 2 points in Manhattan, in the course of the year, you got hundreds of thousands of trips, which means, it means many, many trips every day that potentially could be shared. So we started looking at this. We couldn't do it with traditional mathematics. Linear programming doesn't work when you get such big data. So sometimes you say big data also requires big math. In this case, we work with Steven Strogatz, a friend and a colleague at Cornell University. Steven is one of the fathers of modern network science. And so we use network science to solve the problem. We use this thing called shareability network. And what we discover is actually in New York, we could take everybody to destination exactly when they need to be there, give or take a couple of minutes, but with 40% less cars than what we have today. So with a simple example, we got data that the city made available, we analyzed it, and we found an interesting solution, an interesting result. Now, the more interesting thing is that actually this result came to the attention of Uber. And at the time, Uber had not launched Uber Pool yet. And so they reached out, we started a collaboration with Uber, and as you know, today Uber Pool does exactly this. Allows two people going more or less in the same direction to pool, to share the ride with somebody else, which means, potentially one less car on the road, less congestion, less pollution in our cities. So again, a very simple example. I'll show you many more in the next few minutes about how we can start from data to understand the city. We use mathematics to understand the data, and then the results can help us in a feedback loop to change the city itself. There's a more recent piece of work where we looked at another question. The question for us was, imagine tomorrow we got self-driving cars. They are coming. We're working in Singapore with fleets, huge fleets of self-driving cars with the government. And our colleagues at MIT, I'll show some more work in the self-driving car space together with colleagues at MIT. And so imagine in Manhattan, you are going to move the whole fleet into self-driving cars. Then what is the minimum fleet you need in Manhattan to actually take everybody to destination exactly when they need to be there? In this case, no sharing, just looking at better mathematics. Here's a little video that tells the story. So again, the idea that tomorrow, I cannot control the volume of the sound, but so that tomorrow we'll be able to run a city such as Manhattan or any other city with self-driving car with much less cars than what you have today. By the way, I'm not going into the maths today. I think, because I understand you're a very exciting group coming also from different countries, different disciplines. So I'm not going through the papers, but all the papers you can find on our website. This was the Nature paper last year that where we looked at this and found this solution. Incidentally, as I was saying, again, the same thing. You get the data, you analyze it, you develop maybe new mathematics, and then you use it in order to change the city. So in this case, we just started a company. It's actually the 5th company we start based on the results we've been doing. That's called Data Drive in the US, which is being funded right now in order to take this to real cities. So again, you take the data, you analyze it, and then you bring it back to the real world. And there's something else, so far I showed you just some analysis that we use just by looking at the vehicle on the road actually as a GPS point. So basically, you got cars moving around, the GPS position, you analyze it. But today, the vehicle itself is becoming like a sensor on wheels. Today, every car you have collects 2,000 to 3,000 signals every second with every possible information: the temperature outside, the temperature inside, the ABS if it's in, what you're doing in the car. So the car knows a lot about itself and about the city. And by the way, here you see this a picture that shows you or maps all the sensors of some work we've been doing with Volkswagen on this. And then you can start using the car as an ambient sensing platform. So here again, you map them as a first step, and then you analyze them. This is the analysis we did. We did with the Volkswagen group. I cannot tell you which brand, but you can recognize the city of Ingolstadt. And so those of you who are German understand which brand it is. And you get all this information. For instance, here we're mapping all of this, and we started looking at all the little crosses, which is where the ABS kicks in. And as you know, the ABS kicks in when you're braking very, very hard, and then the car is almost bumping into something, you're braking so hard that the automated way to control anti-blockage has to jump in. And then when you look at that, the interesting thing is that you see the cross, and then you see it once, twice, 3 times. And at some point, you know for sure that a big accident will happen there. And you can actually go and look at those places by looking or by mapping them. And so again, you use this information from the car to understand the dangerous places and potentially redesign the infrastructure, all of those intersections where certainly there's an issue because all the ABS kicks in similar places, all the accidents then correlate with the ABS that kicks in. Another important thing, well, as we all know, climate is becoming more and more important. We're getting all the terrible news about, especially since more recently, about all the latest measurements about climate change. And the important thing is also look at microclimate. If you look at microclimate today, we can measure the scale of the little units that you see, which are still quite big. For instance, if you go on weather underground, that's the size of a unit where they measure, where you get information about weather. But again, if you got the car, you can do interesting models. The car knows the temperature outside, inside. The car knows if it rains. You get a little sensor that actually detects automatically when it rains for the wipers. And so you get all of this, and you can do interesting, microclimatic models with much better resolution about how the car moves on the road. So again, how we can use the car as a platform to sense information. Now, last year, before this happened, you're all probably familiar with this. It happened really a year and a month ago. It was on the 15th of August in 2018. That's a Morandi bridge done by the great Italian engineer Morandi that collapsed next to Genova. And just before that, we actually had a paper, before I go to the Tacoma, I had a paper that did some work on how we can monitor better infrastructure. Now, so you know what happened here, and the investigation is still happening, but certainly one of the reasons for this accident is that the bridge wasn't monitored enough. And accidents like this have happened many, many times. And you've seen many of them. Some of the most famous one, the one I saw at school when I was studying structural engineering, was certainly the Tacoma Bridge, in that case because of resonance. But more generally is something similar to what happened to this bridge, which is close to MIT. That's called the Longfellow Bridge. To the left, you see actually the MIT campus. To the right, you got downtown Boston. Well, Longfellow Bridge was working fine, and then one day some structural engineer went to check it, and they realized it was about to collapse. So they shut it down. The whole city was isolated for few years. The cost of rebuilding it was a few $100 million. And it just opened like a year and a half ago. And you see here they basically redid the whole thing because they hadn't monitored it close enough. And the reason for that, as you all know, that if you want to monitor a structure, it's very expensive. If you want to monitor a bridge, here you see the Golden Gate. But if you want to put other sensors like what you see to the left, in order to look at vibrations, or if you want to see to the right people inspecting the bridge, the cost for an average bridge in the US, if you put fiber, is something that can go up to $500,000 per year. And you cannot do that on all the bridges in the United States. But at the same time, these measurements that you get when you monitor the bridge, we can get perhaps another way. So our idea 2 years ago was, what if we take all the accelerometers we have? We got our accelerometers in our cars, we got them in our phones, we got we can buy accelerometers like the orange box you see there. And we said, could we, through this, monitor the infrastructure? So what we did, we took a car, we used the data from the car itself. As I said, among all the sensors inside the car, you also have accelerometers. Then we put 3 phones and then a professional accelerometer on the top. And then we decided to start moving back and forth on the top of this bridge. And the reason is that the Golden Gate has been studied for so many years, so we know everything about it. And so it's a perfect ground truth. So we started moving back and forth over 100 times. That's why we want to have some good research students on the team. They had a lot of fun, and then after 100 times, the San Francisco police got a bit suspicious of this car. They kept, so they were stopped by the police. But anyway, before they were stopped, we got all the data, and that's the raw data that we got from the accelerometers, and we then analyzed it, and surprise, surprise, then actually we were able to identify most of the key vibrations of the vibration frequencies of the bridge. And if you're interested, there's a paper which is here. It's proceedings of the IEEE from last year. It was just before the Genoa collapse. But the interesting thing is that this was done on the Golden Gate. Then Uber got very interested, and also Allianz. We're working with Allianz, the German insurance company, got very interested. So now we're doing 2 tests, one in the US, one in Europe, where we're getting data from hundreds of thousands of cars, and we're getting the accelerometer data to see if we can, at almost zero cost, do a first scan of all the infrastructure in a country. And of course, this is never going to be as good as the sensor you might put on the bridge, but it's a first scan. It's like when you go to hospital. First, they measure your temperature, and then they look at your pressure. And then if there's an issue, they will send you, and you will do an MRI or an X-ray. So it's a first scan that you can do at almost zero cost by using all the sensors we have in our pockets. Again, I want to show this. When I was invited, I was asked to talk about big data. For me, it's a very simple way where big data, which is everywhere now, can tell us a lot about our lives, our cities, and of course, all the things we build, such as bridges. I'll go very quickly. You can also say a lot about how people drive. Why are you laughing? Well, because probably you can detect that they drive probably in a different way, and you can measure it now. So again, you can look at all the sensors from the car. There's something that, again, insurance companies are very interested in. We call it driver DNA, driving behavior. You can cluster it, use artificial intelligence. You see here basically all the different parameters, how they change. So here you see basically this kind of little thing is what we call the driver DNA. And each of us is actually some of that, and that actually correlates beautifully and in a very scary way with the probability you have an accident. So again, we can learn from this and then try to see how we can learn or teach people to drive better if they're making mistakes. So again, it becomes a way where data can help our behavior. Now, at the same time, I say that the car today has 2,000 to 3,000 sensors, every car out of the factory, but you add one more sensor, such as this. That's called a LiDAR. A LiDAR does a 3-dimensional scan of the city, like the human eye. You feed that into an artificial intelligence system, into a computer with some programming, and the car drives itself. Now, that's not the future, a distant future. As you all know, it's the present. Yes, we're not level 5 yet, but things are happening fast, and there's a lot of there's a lot of self-driving cars being tested all over the world. And when you do that, then things are going to change again, because today, the car is used on average 5% of the time. 95% of the time, the car is there. And as engineers, we need to build all that wasteland. In the United States, we got, if you take all the parking in the United States, the sum of all that is as big as the island of Puerto Rico, which is very big. And then, and the reason is this, 95% of the time the car is parked. But if you got a system where the car drives itself, then the car gives you a lift, and then gives a lift to somebody else in your family or anybody else in the city. So then you don't need to have so much parking. And actually in Singapore, we looked at, in Singapore today, we got 1.4 million parking spots. And if you go to self-driving, that's a paper from a few months ago, we can actually cut it down to 400,000, so a reduction of 70%. We're doing another paper right now to estimate it better. I mean, it depends on some of the assumptions, but still, you can cut it a lot because the car keeps on being used on the system. But other things might change. Now think about the future, a few years from now, when all cars will be self-driving. Then at that time, other things could be redesigned. For instance, this. That's a well-known traffic light. And as you all know, traffic lights arrive on our roads when cars arrive on our roads. But if you got an intelligent system where every car knows where it is and where all the other cars are, then you don't need to stop anymore. You can keep on going, just avoiding collisions, like this. Don't try it yet. I've shown the video in the city of Naples, and they told me, so what is new here? Now, I'm Italian, so I'm allowed to make such politically incorrect jokes, but I need to tell you that the former Italian minister publicly said that in Milan, traffic lights are instructions, in Rome, they're suggestions, in Naples, they are Christmas decorations. All right. Again, that's mathematically is very interesting. So we're working on data collected from Singapore. Again, a lot of big data. We're trying to redesign a traffic light system. Mathematically, we extend the queuing theory to take into account, to model the intersection in a different way. I will not show you the detail, but it's quite interesting. I showed just the beginning, maybe. Well, it's quite interesting. You can really make the system more efficient. What you see to the left and to the right, to the left, the most sophisticated traffic light system we have today, and to the right, the system based on slot. And as you see, the delay per car and cars waiting changes and increases a lot between the two systems. show you the whole video just to stay a bit on time. And if you're interested, again, that's the paper you find. You find all the paper, you can get the full text on our website for everybody. Now, for instance, we are using this in our design office. We're using this in Singapore in a tower where we are redesigning all the parking spaces so they can be converted tomorrow. So you don't need to build something that tomorrow might be useless. From the beginning, we think, well, if tomorrow, because of self-drive, we need less parking space, let's make it compatible to a future when this can be converted into something that looks like this. Or we're also working with Google sister company Sidewalk Lab in Toronto. They're doing a big development, and here we're thinking about, what about roads? That's from our design office, not from our lab. Roads that can actually, in the morning, you can use like this. And then based on data in real time, you can turn it into something like this in the middle of the day, or in the evening, you can turn it to something like this for a party. We're using a little robot like a Roomba, moving pieces around. And if you go to Toronto, you find this where you can look at the prototype and test it and comment it and play with it. At the same time, in Paris at the moment, again, with our design office, we are part of an exhibition, which is at the so-called Pavillon de l'Arsenal, so the Arsenal Pavilion, which is called Réinventer le périphérique, reinventing the peripheric, which is a big ring road around Paris. And here we've been working with Vinci, the big highway group, French construction and highway group, in order to think about a future when the highway can become much more flexible in the way it's allocated, so we can use better real estate in a dynamic way, where we can also use it for producing. Again, there's a few materials that do it today, still expensive, but basically how can you turn that into photovoltaics, energy producing surfaces, and how, because of electric vehicles and autonomous vehicles, what is called AVs and EVs, because of that, the highway is going to be much less polluted, less noisy, hopefully safer, so we can actually build much closer. We can have homes and buildings that get much closer to the highway itself. Now, those are more kind of conceptual images, so I will not discuss how the truss supports the span, but you get a sense. In Amsterdam, we're working with the city of Amsterdam, with the mayor of Amsterdam, who came to us a few years ago, and she was very excited and interested in experimenting with mobility in Amsterdam. But how do you play with mobility in a beautiful city that looks like this? In Amsterdam, in the city center, you have almost no roads, very small roads, but you have a lot of canals. And so we said, well, what about working with, not with self-driving cars, but with self-driving boats? And we call them rowboats. Well, what can you do with them? What can you do with a rowboat? You can use it to move things around like this. You can use it to move people around like this. You can use it to sense the air quality, the water quality. But also, you can use them like a responsive, flexible infrastructure for the city. Imagine all the robots that actually become like floating elements that can combine to create a temporary bridge or a floating stage or other things. So that was the initial idea, which is actually, in this case, it was inspired from what the city of Venice has been doing for a long time with gondolas doing a temporary bridge over there. So we're now building the robots. We've been working on this for 3 years, developing the intelligence, the self-driving capability. The robots themselves are designed a little bit like drones. So they got 4 engines. They can push in different directions, and so they become very easy to control and much more maneuverable than traditional boats. We put the engines like this at the beginning. We tried with water jets like this. That's the first 1:4 scale model. The final model is 4 meters. This is close to a meter. You see it here being tested on the canals in Amsterdam. This is very controllable. Show another video. It can also move laterally. We told the mayor, well, the research might also fail, but in the worst case, we'll open a toy company, because everybody seems to have so much fun playing with this on the canals. So I'll show you briefly, by the way, in more detail, what I was saying before about how this works. So this is actually the LiDAR I showed before, collecting big data, 300,000 points every second about the city. So this is how the robot sees the canals. Anybody from Amsterdam here? Raise your hands. Yes. Is your home there? So you see all the point collected, the cloud, and that's what the machine uses to navigate. But if you combine it, you also see the city in a different way. So if you combine this and aggregate it, you see the whole city in 3D, which is what you see here. Little by little, you get the whole 3D of the city. And just something again that might be interesting and relevant for a lot of you is, data always, you collect data for one reason. In this case, we are collecting data because the machine, the boat, has to move. And the data is the input, the visual input for the boat to move. But then when you're doing it, as you just saw, you're also scanning the whole city. And so what we are trying to do now with the city, you're getting very, very precise. Across the canal, you're making measurements. Every time there's a little boat, you're making measurement with the precision of, say, 1 millimeter. And so what you can use it as well is about looking at one of the problems in Amsterdam is that the facades of buildings tend to move because of problems with foundations like in Venice. And so you see that a lot of the facades in Amsterdam are actually tilted by, they have an overhang that can be quite significant. And the city wants to monitor that. That becomes also a very interesting way to keep on monitoring structurally all of the buildings in the city. What you see here, by the way, is a bit more technical. It's about how the boat moves. So the boat gets the three-dimensional scan that you see there. And the boat knows the destination, which is the blue line, but has also a number of alternatives, which are the green lines. And so when there's an obstacle, then the boat will decide to take an alternative path in order to go to the destination. So that's how every self-driving car works, or the self-driving boat works. And if you look at this, we actually had a lot of fun in the swimming pool at MIT. So you see here, if you look at this developing a control system in order to make sure that the boat follow the right trajectory. And between self-driving boats and cars, things are similar but not exactly the same. For instance, we think we can be at level 5 very quickly here. And the reason is that two things are important for level 5. Level 5 is when the boat can do anything on its own. The first thing is about speed, and the second is the complexity of the environment. Now, on the canals, it's a bit easier than on the road, because the speed is limited in Amsterdam, is less than 10 kilometers an hour. And then the complexity is not as complex as a big intersection in a city. Now, at the same time, other things like this are more difficult, because here the response of the boat can actually change all the time, because there's a wave or people can move from one side or the other, so the center of gravity changes. So you need to constantly calculate the response. While with the car, the response you calculate at the beginning, and then it's almost like fixed, because the weight of the people doesn't change much how the car will behave. So again, there's interesting differences between doing a self-driving car and a self-driving boat. We're also developing a system for them to collect and to latch, to connect to each other, and to latch is a system. It's a mechanical system like this. You see them here being tested. The students love them. They call them the kissing boats. And the kissing boats, we're scaling up to full scale and using different applications, looking at waste in Amsterdam, how we could collect waste with this, how we can also collect waste on the canals. There's Waternet, which is the company running taking care of the water in the canals in Amsterdam. Just apologies. So, they're doing a bit of cleaning, so we are trying to do that with an automated system like this that's being prototyped. And so working on this. Now, I want to show you a couple of more things to finish. The first one is that, I focus on mobility, and many people think that tomorrow we can also do cities almost without infrastructure. Actually, I know that our common friend Norman Foster, who now has the foundation here in Madrid, is not here today. There's somebody from the office of the foundation here, but he's doing a project with us at MIT, really looking at the city without infrastructure. Can you do a city where you don't need infrastructure anymore? Infrastructure is built in a bottom-up way, or if you're moving with drones, you really can do no roads. You can live without infrastructure. Now, I think that's a very interesting research question, but at the same time, I don't think that this will be the solution for cities tomorrow. And the reason for that is that technology can change many things, but technology cannot change one thing, and that thing is physics. And physics, as you all know, means that if you take your weight, my weight, and you want to keep it in midair, let alone move it, just to keep it there, you need a lot of energy, you move a lot of air, and you generate a lot of noise. and there's no way around it. Yes, we can do a bit of noise cancelling tomorrow, but I think those three things are physics. And then, if you think about what happens with helicopters today, in Manhattan, there's a few tens of flights taking off every hour from the different helipads in Manhattan, and everybody complains. But if you want to have a bit of impact on Manhattan in terms of transportation, you don't need tens of flights an hour, you need tens of thousands, 1,000 times more. That will never be possible. Let alone the fact that in Manhattan, as you might know, they remove all the helipads from the skyscrapers after a famous accident that happened on the old Pan Am building. Now it's the MetLife building in Manhattan, where actually a helicopter landing from JFK was landing. There was bad weather and ended up on the road, and actually there was I think a few people were killed both in the helicopter and on the ground. So I think if you were to multiply the number of flights by 1,000, that could be really an issue. So I don't think that will happen. Will be a solution in Madrid and so on. Will be very interesting in Africa. Will be very interesting in the countryside. Will be very interesting for smaller things. For instance, we are working with this is our design office again. We're working with the Italian Highway Authority, in this case, to work on drones that can sit and sleep on the top of those poles. And then when you got an accident, you can send them out, and they will monitor and look at the situation. So it's like a system you can deploy based on need when you need it. Or we're working on the MIT campus to solve a very important problem. You need to know. The MIT campus is not as beautiful as the Torroja Foundation. The MIT campus was built by American engineers a bit quickly. Every building has a number. It's a bit messy. And for instance, I'm in building 9-50, and sometimes I send people to computer science, artificial intelligence is building 36. Daniela Russ, who's I think 236, and people get lost on the way. So we developed this project with drones in order to help them, and in particular, to rescue Harvard students.
Welcome to MIT. Where would you like to go? Follow me, please. Computer Science and Artificial Intelligence Lab is the largest research lab at MIT.
To your right, the Media Lab. To your left, the Data Center.
Follow me, please. Approaching your destination.
You have arrived. Welcome to Sensible City Lab.
Goodbye.
Anybody from Harvard in the audience? No, they're all scared now to raise their hand. I need to tell you a funny story. That actually the guy who was playing the dumb Harvard student was actually from Yale. And as you know, Yale and Harvard, if you're in American culture, a bit like Oxford and Cambridge, this kind of big rivals. He was very happy to play that role. Now, we have a few more minutes, and I could actually flood you with more slides. But instead of that, I thought it would be great to have a bit of discussion. So, if there's any thoughts, ideas, questions, or to have a bit of conversation together, we can use the remaining time for that. So I will stop here. I thank you, and let's have a bit of debate. Thank you.
Thank you very much. This might have been an eye-opener for several of us. And he is so kind to open for questions and discussion. So please.
Thank you. I see a hand there. Do we want to do it with a microphone? Or I think if you just maybe say, if you can, I think everybody can hear you. If not, I will repeat your question. Yes.
In the last movie, how did the drone open the door?
We're still working on that. but I showed you also. I showed the presentation mostly with the movies. By the way, we like to. We always do mixed teams. So in our teams, you'll have people who do maybe mathematics and physics, working together with engineers and with designers. And so we want to also to, of course, do research, but we also want to be able to make sure that what we are doing is available for the broader public. And that's why we also do the movies, which, there's always a scientific paper behind, but there's also a way to communicate to the broader public. And we think that it's important because, doing that means engaging a community, say the citizens, about what type of city we want to build. For instance, the discussion about drones, of course we can do all the mathematics and see what is feasible and not, but I think ultimately it's a decision we all need to make collectively. So that's why we put a bit of time also in doing the movies, and I put the papers here, the scientific paper, just in the background. You find all of them on our website. But going back to your point, in your question, which was ironic but nice, it's about to do that. You still need to develop a lot of things based on today's technology. For instance, indoor navigation is not solved yet. When you're indoor, you don't have GPS, so you need to find a locationing system. We've been doing a lot of work based on this in order using deep learning. You might be familiar with deep learning, CNN, in order to detect the environment and find a new way to orient yourself, which is what we do as humans. So when we are inside a building, we know where we are by looking at the features. And so we're doing that in order to do that. And so that has led even the little movie to achieve some of that. There's a lot of exciting research that you need to do. And again, you can find it on the website. But for us, it's important that in every project there's a bit of both components, because yes, it's about the research, but also about the discussion about what type of city we want to build and live in. Yes. Oh, many hands. Yes.
Very impressed with your all of the things that you've done with the technology. Are you at all concerned about the contribution of all of this to the dehumanizing of life? For example, if I were lost on MIT campus, I would ask a student, and it would be probably a very nice human interaction. I don't want to deal with it.
It's a very good point, and actually I think that's the core of what we want to do, because I think Bucky Fuller taught at MIT in the 50s for a year, and he was, as you all know, an engineer, an inventor, designer from the 20th century. Bucky Fuller said that there's only two ways to cope with the future. One is to be victims of the future, and the other one is to be architects of the future. But if you want to be architect of the future, I think you need to engage with the technology, and sometimes we're using the technology also in a way that can be ironic or paradoxical. I didn't show it to you, but actually one of the first projects we did at the lab, we did for the first time ever, was back in 2006. Because of this, the project led to scientific publications, but was debated in all the broader media, from The Economist to the Financial Times, because it was the first time that was done, that we took a big city and publicly showed how we could track phones from millions of people in the city and describe the city as a living organism. As a matter of fact, what you do today with Google in your phone, some of that is based on some of the papers we did at the time that use the phone, aggregates them, and look at movement. And we did it not because that's the future we wanted, but we thought because it was important to have a conversation. So I believe that even if there's something that we don't like, it's very important to study, to look at the consequences, to make it public. Because only in this way, and I think that's really our role, what we can do, only in this way we can decide where to go, where not to go. If we just decide that that part of the technology we're not interested in, then we'll be victims of the technology and in that future. And I think so it's important in some cases, but you're right, we also look in the future and don't need to be only utopian. It's a little bit, many of you might be familiar with white hat and black hat hackers. Now, white hat hackers are the good ones. They're the ones who look at the vulnerability of a system, highlight it in order for somebody to fix it and make the system more robust. I think sometimes we have a similar role, which is the fact of looking also at things that might become bad. Maybe some technologies might dehumanize us, but we want to study them as well, so that maybe we can create antibodies against that direction. If we don't do it, if we just say, oh my God, I don't want to even to look at that, then we'll be victims of, most likely victims of the technology. We will not have the antibodies to cope with it when it comes. And so I think that's how we see things. But I like your point. We don't all of what you've seen, and we did this in the last book we did that was published by Yale a couple of years ago, called The City of Tomorrow. We talk about this. We call it future crafting, the idea of experimenting but opening up to public discussion, because only like this we can decide together what type of future we want. I saw a couple of other hands. Yes, one here.
Yeah, so you talk a lot about autonomous vehicles.
Yeah.
And for example, the intersection analysis that you did. So on one hand, you had people driving all the vehicles. On the other hand, you had autonomous
Yeah.
vehicles. What challenges do you see in the transition between one and the other, where you have a combination
Yeah.
of human error versus autonomous vehicles?
Yeah, thanks for asking. So I think there's two phases. Now, when you want to get to the intersection, as I mentioned in the beginning, when I was talking about intersection, that can only happen when everything is autonomous, or if you define a part of the system where everything has to be autonomous. For instance, Singapore has been discussing of making Singapore that has a lot of urban highways, and the government has been exploring, entertaining the idea of saying, well, maybe at one point we'll say there it's only autonomous, nobody else. So you can only do that when everything is autonomous. But in all other conditions, however, autonomous car is autonomous, as the name says, because really can do anything like a human. And so the idea is that you're simply replacing a human brain with an artificial brain. So it can really, the coexistence is not an issue. It is actually there by design from the beginning. But things are changing very fast. And I'll tell you just a little anecdote that I have two colleagues in economics at MIT. They are some of the smartest economists on campus. I think one of them is one on the Nobel, is always mentioned the Nobel laureate, possible awardees. And in the early 2000s, they did a paper where they explored the impact of technology on jobs, big topic, and they listed also what they thought at the time were safe jobs. That was like 15 years ago. And out of safe jobs, they actually listed drivers, truck drivers, and so on. Just 15 years ago, people couldn't see this coming. And the first big autonomous driving, self-driving piece of research came because of a DARPA challenge. I believe it was in 2004, where DARPA did a competition. DARPA is a big funding agency in the United States, related also to the military. And they did a competition that was about, can you drive a car autonomously? At the time, just 15 years ago, the MIT and Stanford came, the top three were, I don't remember if it was MIT, Stanford, at Third University. And I knew very well the team who was doing it. I wasn't part of it. But actually at the time, the whole car was like a big SUV. And the car would drive itself, and the whole SUV was packed with servers and computers. We're just full of that. Today you run the car with something that's this small, probably. So just to tell you how fast things have been changing, that has been a very surprising thing. And again, from the beginning, from the DARPA challenge initially, the combination of human and machine has been by design the starting point. Yes, I see. How much more? What time do we?
Shall we take one more question?
Why don't we take the remaining question and summarize them into one answer? Because I see three hands. Yes.
Yes, thank you, Carlo. It was amazing. But I would like to say that in the future it seems that we will not be able to clean more roads because we will make more efficient traffic. Many of our normal activities will be reduced, but I am sure that it is not the case because we need to take advantage of all the information we have. And I would like you to give us one example. How do you think this new technology, big data, could affect our activity? We are talking now about conceptual design.
Yeah.
We start with a few information,
Yeah.
but you are given exactly the opposite. You collect a lot of information and you get conclusions. How we can combine both?
Yeah. Maybe it's such a nice question. Let me answer this one, then we take the other two and I combine them because it's so two hands. So for the first thing, well, the fear of being out of jobs, it is possible we will all be out of jobs. And for instance, we are seeing more and more artificial intelligence being able, it has been if you look at the past thousands of years of humanity's development, it has been the same thing. we took some activities we were doing, we let machine do it, and then we would concentrate on things where humans would be better. So for instance, you take in the beginning, you learn about the wheel, and you learn that it can be animals doing that, and you in agriculture use that. It's much stronger than a human, but we can focus on thinking, on farming, and so on. So we can focus on the things we do better. Now, the difficult thing, so this has been happening for a long time, and has been happening very fast. If you think about this very place where we are, if you think of Spain or Italy, like 100 years ago, over 90% of the population were farmers. And now those jobs have disappeared for over 90%. And now in Italy it's less than 5%. I don't quote me on this data, but because I didn't see the latest one, but we're talking about something like 5%. So I think those changes always happen. The big question is what happens if at one point machines can be not only stronger than us, like the old machines of the first, second industrial revolution, but actually machines and computers can become better than us in almost every respect. And that's a big question. And I think, I think probably that would take a whole new conference to explore. I'll tell you a couple of things. One, a guy I respect a lot, who was actually one of my professors, not really for the PhD, but was going to his lecture at Cambridge University. He is Martin Rees, Lord Rees. He's the Royal Astronomer in the UK. And so he had an article 2 years ago where he said, well, in the end, what he calls electromechanical intelligence is much superior than organic intelligence. It can go abroad in the universe. We cannot. We would die before we reach out there. The amazing thing about self-driving cars is that they don't have that terrible things about human life, which is that when you're 18, you need to make again the same mistake. Every generation has to make the same mistakes. They can tell you, if you do this, you bump into a wall with your car. But you will do it until when you bumped into the wall once. We've all done it. Then you haven't learned. You need to learn it on your skin. You can learn something through reading, but you never learn 100%. While if you got 1 million self-driving cars and one makes a mistake, everybody else learns in the same way. So I think his point was, electromechanical intelligence is much superior, and so it should take over. We need to disappear, they take over, and they are our progeny, so it's fine. We created them so that we can let them go. There's another, it's a possible view. There's other views, maybe more reassuring, that we can think about integration. Basically we use technology to augment human, but certainly it's an important question we should all debate. The second part of your question is about data. Where do you start? I think it's going back and forth. When I was coming here, I took a picture of a beautiful sentence by Torroja outside, which I will read to you. The first one, the first one I encountered on the way, which says, antes por I think that's a solution to your answer. It says, antes y por encima de todo cálculo está la idea, moldador del material en forma resistente para cumplir su misión. So he says before calculation, you need to come up with an idea. And that's the same with big data. You start with a question, a hypothesis or something, then you put your hands in the data and you see if it works, and you go back and forth. And I think what Torroja was doing here in a masterful way a few decades ago. Thanks. Should you stop? Or can I still take the remaining two, and I'll be very quick. Yeah.
Very quick.
Privacy, okay. Well, you said quick, okay? And it's yeah. So the software, the first company that started doing it on a big scale was Uber, and they did it based. I mean, that was inspired by the work we did, and then we've been collaborating on the past few years to really work on all these algorithms for ride sharing. So and then Uber has inspired many other companies. So now today, if you use a Via in the United States, if you use Lyft and so on, many of them have ride sharing. So actually, that was an example of how you go from big data to an idea, to measure it, and then they can go back in the real world just by collaboration with private sector or inspiration of other people. So we're totally part of that, and Data Drive, the new company we started, wants to do it with a slightly different model, to optimize this in a more systemic way in the city. And I'll finish with the last point about privacy. Now, I cannot be quick, but I will say, well, if you want me to be quick, I will tell you just something they told me in Silicon Valley recently, which is privacy is dead, just some people didn't notice. Unfortunately, it's true, but it's not very bad news. It's true because since the smartphones arrived, we're talking about 2009, 10 years ago, then if you got this in your pocket, this collects thousands of data points from you every day. It knows exactly where you are, what you're doing. It has the accelerometer. It knows if you're moving by foot, by bike, by car, by train. If you're horseback riding, you can detect, with your paperwork, you can detect this if you are trotting or galloping just by your phone. So all this information is stored somewhere on the internet. And so privacy, effectively, it is dead. The problem is not anymore that. The problem is that only a few big companies and big states have access to the data, and many others have not. So I think the problem now is the problem of democracy. And I finish, hunter-gatherer societies used to live without privacy. So I think it might be okay. I don't think there's a way to put the genie back in the box. So we might need to cope with this, but we need to all be part of the conversation about how we can do this in a more democratic way. So it's a very important problem. We should fight for it, but not anymore to try to save a privacy that is dead, but try to understand how this can lead to a more fair society. Thank you.